So we're talking about when to use the normal approximation to the binomial, right? So how do I know when I should be using the binomial to begin with? When I have
n number of trials.
We need n number of trials. So the idea is n is given to us. So a certain number of trials that we're working with. And at each trial, I can have a success or a failure, right? The probability P is constant across trials. So when is that the case? When I'm flipping a coin, for example, it's always going to be a 0.5. Let's think about it this way. What if I was doing something where I sample a student among you guys? What's the probability that that student is male, let's say? So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 14, 15 students right now here. And of those, 1, 2, 3, 4, 5, 6 of them are male. So the first try, what's the probability that that person is male? 6 out of 15, okay? Then we tell that person, okay, you stand over here now. What's the probability that the next person is male? 5 out of 14. So what happened? That probability changed. So that wouldn't be a situation where I would be using the binomial. If I'm sampling without replacement like this, what's happening is the probability of selecting a male isn't constant across, right? Versus when I'm flipping a coin, the probability of a head is always 0.5, regardless of what happened in the previous setting. Or if I was doing the sampling situation and I was sampling with replacement, so you grab somebody, then you put them back in the bag, and then you're selecting again, then the probability would stay constant as well. So that's what we mean by probability is constant across trials, and your trials are independent. And pretty much, if your probability is constant, chances are that's happening because your trials are independent. So those go hand in hand, okay? So let's think about a situation where we may need to do that. Let's say that I have a situation where n is equal to 1,000, okay? My p is equal to, let's say, 0.30. And I'm looking to see what's the probability of at least 800 successes, okay? So my number of successes should be 800 or more. In this case, we do have a binomial situation. Given number of trials, P is constant, everything is either a success or a failure, and I have independent trials. So how would I calculate this using a binomial? One of the common mistakes students tend to make would be to write this out as such. Here is 1,000, 800, 0.30 to 800, 0.70 to 200, okay? Now this doesn't look absurd, but there is something wrong with this. This is not the solution to the problem that we're looking for. Why is that not the solution to the problem we're looking for? Yeah?
It's just the probability that k is equal to 800.
Exactly. This is only the probability that k is exactly equal to 800. So if I wanted to use this type of an approach to calculate the probability that we're really asked for, I would have to do a lot more. I would have to apply the same binomial formula for 801, for 802, 803, all the way up to 1,000, and add all of those up. Because what k is greater than or equal to 800 means really is k can be equal to 800, k can be equal to 801, all the way up to k equal to 1,000, right? But that's not what I'm trying to, well, that is exactly what I'm trying to do. It's just going to be very tedious to go through it using the binomial distribution, because the binomial formula, which is probability that k is equal to some number, and choose k, p to the k, 1 minus p to the n minus k. This can only be used when you have an equal sign here, for exact probabilities, not for ranges, okay? So if you want a range, you would have to calculate exactly what the components of that probability are and add them up. So we said that in these situations, it might be possible to approximate that binomial with a normal distribution. We showed on that distribution calculator applet, for example, how when you increase the sample size, the binomial like probability histogram, which looks, as you increase your sample size, it's going to look maybe something like this, right? And basically, instead of calculating a range of probabilities as individual binomials and adding them up, we might be able to say, hey, you know what? This looks sufficiently like a normal distribution. I'm just going to calculate this area and call it good, approximating it, okay? The thinner those bins are of those histograms, as you can say, the more closely the smoothed curve is going to look like that. And they get thinner and thinner as you have more and more observations. So basically what we have here, the black, the histogram is of a binomial, and the red, the smooth curve, is of a normal. And they're overlapping exactly on top of each other, which means they must have the same mean and the same standard deviation. We also know that when we're working with the binomial distribution, the mean can be calculated as n times p, that's the number of expected successes, and the standard deviation can be calculated as n times p times 1 minus p. Does that sound familiar? So, if I know that that's how I would calculate the mean and the standard deviation of the binomial, that's the histogram, black histogram underneath it. And if I'm saying that the red curve, which is a normal, is going to have the same mean and the standard deviation, and I'm looking for that red shaded area, a range of observations under a curve, under a normal curve. If I know the mean, I know the standard deviation, I know exactly what this cutoff point is, anything beyond 800 we said, we should be able to easily calculate that, right? Because that just becomes a normal problem of, here's a distribution, you have an observation, find the area under the curve, right? When I draw my normal curve, the first thing I want to do is mark my mean. So in this particular case, we said we can calculate the mu as n, which is 1,000, times p, which is 0.30. So that comes out to 300, right? So mu for this distribution is equal to 300. Okay? And the observation at which we are drawing our, like kind of our cutoff is 800. So if I want to find that area under the curve, what am I going to do? Yeah?
I had a question.
Yeah.
Obviously in this situation, it's pretty obvious that like the n times p is greater than 10, but do we still need to like show that in our...
Yes, so you would want to, because the fact that we can do this approximation is because we have a sufficiently large sample size. And we define a sufficiently large sample size to be able to approximate the binomial by a normal as with the success-failure condition, which is n times p and n times 1 minus p needs to be greater than or equal to 10. You're right. You should actually, if you're using that, you should put that down on your paper. Okay? So how do I find that red shaded area? We need a z-score. For my z-score in the numerator, what do I have? An observation? What's the observation here? 800. A mean? What's the mean? 300. And in the bottom, what do I need? A standard deviation. So let's go ahead and calculate that standard deviation. So that's going to be the square root of 1,000 times 0.30 times 0.70. I don't know what that is. Yeah, but then we need to take the square root of it. So let's call it 14.5, okay? All right? So that would be what goes in my denominator, 14.5. Okay? So this comes out to be 500 divided by 14.5. Without looking at a table or anything, how big do you think that area is? that shaded area. I mean, not based on my figure, based on what that z-score is going to come out to be.
Because you can't see it.
It's going to be tiny. This area is probably just almost 0. How do I know? This is going to give me a giant z-score, much bigger than 3 or 4 standard deviations from the mean. So really, if I was drawing this to scale, it probably would have looked something like, here's your 300, here is where your 800 is, okay? Tiny, tiny area after that. All right? Yeah?
Can you go over number 10 on the practice midterm?
Let's go over number 10 on the practice midterm.
Really quickly.
Yeah?
So for an instance like this on the exam,
Uh-huh.
do we have to calculate the actual z-score, or can we leave the fraction and say the z-score is huge, therefore that space is a 0?
If you're going to actually put down z-score is huge, much bigger than 3 or 4 standard deviations or so, and hence the area under it will be 0, then that's perfectly fine. If you have no indication of that particular reasoning, then that wouldn't be good enough. Yeah?
If we have a large sample on a binomial distribution and it's not asking you, like at least as many, it's asking exactly, do we have any way to do that without the choose function?
No, but if you're using the binomial distribution, there is no way of doing it without the choose function, whether you have a small number of trials or a large number of trials.
So you just wouldn't give us one that was too large to compute, because you couldn't approximate it using this method, right?
What do you think?
No, I was just making sure there wasn't like another method.
There isn't another method, and I'm not that evil. I don't know when you will learn it. No, I'm not going to give you something that your calculator's going to choke about. So if we had actually asked a question, this same question, where you actually had to do this calculation, let's say, okay, exactly 800. I'm not going to ask this to you because actually some of you might have calculators who can do that, and some of you might not. And what I put on my syllabus is, as long as you have a calculator that can just do square roots, you should be good in this class. So I'm not going to ask a question where your calculator comes into play. If we are giving you some sort of work that you're allowed to use R for, I might ask you that question, because then I know we have something unifying you all. Doesn't depend on how much your calculator costs. Some resource given to you from the class that you can do it with, but that wouldn't be on an exam. Okay? All right. Any other questions about this before we move on to the other question? Okay, so you had a question on number 10. Okay, ask me some questions. So what are we trying to do here? Explain to me what we're trying to do here.
So for part A, it was asking just what the median of both the different treatment groups were.
So let's find their medians. What's the median for the calcium group?
4.
4. How did you decide the median for the calcium group is 4?
Canceled out until I got to 1 and 7, added 1 plus 7 divided by 2.
So the middle numbers here are 1 and 7, so the median should be the average of those, so that's 4. What's the median for the placebo group?
-1.
Huh?
-1.
That's the -1, so the median for the placebo group is -1, right? So we would like to test if the median change in blood pressure is different for the calcium and placebo groups. What are the hypotheses? What should my null hypothesis say?
Median of C equals median P.
The two medians are equal to each other, right? And let's define median as the population median, right? Because we're not talking about these sample medians here. It's just we don't have a good notation like mu and x bar for median, so let's just define that. What's my alternative hypothesis going to say? Median C does not equal median P, right? Then what is the point estimate associated with these hypotheses? When we're doing a comparison like this between two groups, another way you can think about writing these hypotheses, and just either way is fine, but another way we could think about it is that the difference is equal to 0 and the difference is not equal to 0, right? one advantage of thinking that way would be it would become very clear what the point estimate is, because you know exactly what the parameter you're looking for is. So the parameter that we're testing about is median C minus median P. What is the value of that parameter that we got from the one sample that we have collected? So what is the difference in the sample between median C and median P? That's 4 minus 1, 5. So, yeah?
How did you know to subtract the placebo from the?
You don't have to. We could do it the other way around if you wanted to.
Then what is the result from that?
Sure. So let's say this is approach A, and approach B could be median P minus median C is minus 1 minus 4. That would be negative 5. It doesn't specify which one. Either of those should be fine. Okay? Does that make sense? Yeah?
When we write out the hypotheses, is it okay if we just do it like that rather than, do you want us to write like a sentence, like describing?
No, like we were discussing in class, I think yesterday, I don't want you to do anything, first of all. I want you to do what's right. And what is right is all necessary details. So if you're using notation, you should specify what your notation means. Or alternatively, if you're writing it out as a sentence, how could I write out my null hypothesis as a sentence that contains all the information that we need?
The median change in the blood pressure of placebo is equal to median change in blood pressure.
Exactly, for the entire population. Okay, so in my opinion, writing things in words is a little more time consuming because you want to make sure that you note things like you're talking about the population, not the sample, but there's nothing wrong with it. You definitely don't have to do it both ways. If we're asking you to do it both ways, we would clearly say that in the question. Okay?
I don't know.
Theoretical methods do not apply to sampling distributions of medians, right? We're doing a test for medians here. We use a randomization test. To do so, we write the change in blood pressure on 21 index cards. Then we shuffle these cards. Where did the number 21 come from? That's how many people were in our study combined in the two groups. Then we shuffle these cards and split them into two groups. One of them is size 10 and the other one is size 11. Right? We calculate the difference between the medians and the simulated calcium and placebo distributions. In this case, it's saying, remember that we're calculating it as a calcium minus placebo. So going forward, we should go with that estimate. Up there, as long as you're showing your work, either of those would have been okay.
How do you know when you're doing a simulation like this, which group should be first, like for the cards? So which one?
It doesn't matter.
So you could have done.
This could have said placebo minus calcium.
No, sorry, not for that. For when you're dividing them into the different groups.
Like which one? Like 10. The first 10 is calcium. The second 10 is the rest of the 11 is placebo. Is that what you mean?
Keep going, and I'll see.
No. So I have 21 index cards. I shuffled them. Now what should I do next? I split them into two groups. Are you saying, how do I know which one of them I will call the placebo versus?
I guess in other examples there have been multiple variables, like on the problem set once there was like people who had the treatment and died and people who had the treatment and survived, and you had to
So what you need to decide is which one is the explanatory variable. So I think the non-confusion here is coming from clearly one of the variables is numerical, so you can't divide it into groups based on that numerical variable, so you're not going to accidentally make a mistake. What if we had a situation where our variables were died or not, control or treatment? So then are you going to put into groups based on died or not, or based on control or treatment? We're doing that based on what we note on the cards is the response variable. what we're splitting into groups is the explanatory variable, because we're trying to simulate the actual experiment that was done. And there, individuals were in groups based on whether they took the calcium or placebo. Does that make sense? So then we record this value. We find that difference and we record this value. And it says we repeat this 100 times to build a randomization distribution, which should be centered at what? Where does that 0 come from? The null hypothesis. We said that we're going to be setting, in the null hypothesis, we're setting the difference between our medians equal to 0. And we do a hypothesis test assuming the null hypothesis is true, so that should be the answer. Lastly, we calculate the p-value as the proportion of simulations where the simulated differences in medians is. What's the definition of a p-value? It's the probability of observed or more extreme outcome given the null hypothesis is true, right? Given the null hypothesis is true, we already took care of this by simulating, assuming the null hypothesis was true, by getting a simulation distribution that's centered at 0. So what was my observed outcome? 5. And how do I know it's the 5 and not the -5 for this particular scenario? Because the order is given to us now. So 5 is the observed. What does more extreme mean in this scenario?
Greater than 5.
5 or more, or 5 or higher. I'm not done. And -5 or lower. Why? Because my alternative hypothesis was two-sided. If my alternative hypothesis had a greater than sign, I would only take the first part of this.
So doesn't that mean that calcium minus placebo doesn't really matter?
It doesn't really matter. You're right. It doesn't really matter. If it was a one-sided, though, it would matter in terms of where you're looking at. So, does that make sense to everyone? Then if that makes sense, this should be easy. Because it says calculate the p-value, and earlier you wrote out very clearly how you think the p-value will be calculated. So how would I go about calculating the p-value here?
Count the things above 5 and below negative,
Yep.
or and at 5.
So at or above 5 and at or below -5. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. So then I counted 17 of them. What's my p-value? That's the proportion of simulations, and we're told there are 100 of them, so that should be 0.17. Refer back to the question, is there a difference in median change in blood pressure for the calcium and placebo groups? What does the p-value calculated in the previous question suggest? Which one? Number 2. We would fail to reject the null hypothesis because that's a high p-value. We usually compare it to a 5% significance level if one isn't provided. There isn't sufficient evidence of a difference between the two groups. So what if somebody asked you, yeah, you're claiming there isn't sufficient evidence, but we just saw in our data that there was a difference of 5. How do you explain that? Yeah?
You can assume that the significance level is set at 0.05, and the p-level to be calculated is significantly greater than 0.05.
So at this particular significance level, we're not finding evidence, for example. But how do we explain then if somebody's saying, yeah, but you're saying there isn't, but in the data, we saw that there was a difference.
Just random chance.
This particular sample had a difference of 5 between the placebo and control groups. This clearly was not due to a statistically significant effect of the calcium, but was just due to chance. Because even if it is true that this calcium treatment is completely worthless and will not make people feel any better than a placebo would, You can still observe differences between the two groups, but they might just be due to random chance as opposed to a statistically significant effect.
Can you say, I know we talked about like something not having practical significance, but like in this case, could we say that there's a practical significance but not a statistical one?
We would not say that there's a practical significance but not a statistical one. It's mostly the other way around that we're concerned about, because the thing is, when you say statistical significance, you're making a comment about the whole population, about some truth, versus all we observed was just one sample. So all we can say is, yes, we definitively did observe a difference in this one sample, but the underlying reason for that is just random chance as opposed to effectiveness of the calcium treatment.
So the only time we would ever talk about practical significance is
when you already have
it is
statistical
statistically
significant.
But it doesn't really make that much of a practical.
Exactly.
5.5.
Exactly. Yes. Yes. Yeah?
Distribution of a random example like the one above.
Uh-huh.
It's going to be centered around 0.
This is going to be centered around 0 if your null hypothesis had set the difference between the parameters to 0. Oftentimes, when you're doing a hypothesis test like this and your goal is to compare two groups, that's going to be the case. We will see later in the class that we will have null hypotheses where that's not equal to 0. So it's better to think about this as it will always be the null value as opposed to saying it will always be 0, because whatever is in your null hypothesis, then you can put that in there.
The information, I was under the impression that up to this point, the null hypothesis, we could still have null hypotheses where it's not, where a particular observation is greater, less than, or equal to the sample population. Is that true or not?
So we can have the null hypothesis should always have an equal sign in it.
Should always have.
Should always have an equal sign in it. So what we have learned in this class so far is for scenarios for a one mean, we have learned mu is equal to some number. We've learned how to do that using central limit theorem based methods. For any other situation, so for example, for something like P1 is equal to P2, so on and so forth. Any other thing, we've learned how to do this stuff using a simulation method, but we have not yet learned how would I deal with something like this using a central limit theorem, so a formula-based method. We will learn that in the next unit. Okay? Yeah?
We go over a problem in the book.
Yeah, we can go over a problem in the book. Which one?
3.27.
3.27.
Particularly B and C.
Mm-hmm. Okay. So this is 3.27. We are told that about 70% of 80 to 20-year-olds consumed alcoholic beverages in 2008. So we know that our P is equal to 0.70. We now consider a sample of 50 18 to 20-year-olds. I'll switch it in a second. So N is equal to 50. Okay? So part A is asking, how many people would you expect to have consumed alcoholic beverages with what standard deviation? In this sample of 50, what is the expected number of people that would have consumed alcoholic beverages? 35, right? Now, this doesn't mean that every time you get a random sample of 50 18 to 20-year-olds that exactly 35 of them will have consumed and exactly 15 of them will not have. This number will have some variability around it. And we calculate that with the standard deviation. How would I calculate that standard deviation?
Square root
Because this is a binomial that we're using here, basically, right? Given number of trials, probability of success is the same for everyone, independent trials, so on and so forth. So this is going to be, what does that come out to be? Square root of 50 times 0.7 times 0.3, 3.24. Okay? Now we're asked in part B, would you be surprised if there were 45 or more people who have consumed alcoholic beverages? Right, if we got a random sample of 50 people, 18 to 20-year-olds, and 35 of them said, yeah, I have consumed alcoholic beverages, we would not be surprised at all. 36, maybe we'll say close enough. So at what point might we be surprised? More than 2 standard deviations away is usually what we define an unusual observation as. So is 45 more than 2 standard deviations from the mean? How would I calculate that?
45 minus 35 divided by 3.24.
I think the answer is probably no. 3.24? Oh, it's actually 3.08. So 45 is 3.0, actually 09 standard deviations above the mean. So surprised or not? Yeah. Part C is asking, what is the probability that 45 or more people in the sample have consumed alcoholic beverages? So if I actually wanted to calculate, what's the probability that K is greater than or equal to 45? How would I go about doing this?
You have your z-score from part B, so if you want greater than or equal to 45, you want things that are 45 and then up under the curve, because once you check that it's normal distribution.
So very good. So we need to check, can I draw this? Okay, because if I can draw that, I can easily calculate that area. So how would I check, can I draw that normal curve? So 50 times 0.7, obviously greater than 10. 50 times 0.3, 15 also greater than 10. So we're good that we can actually approximate this binomial with a normal distribution that has a mu of 35 and a sigma of 3.24, right? So here is my 35. I'm looking for this area. We already calculated the z-score for this. That's exactly what we did in the previous part. We never used the word z-score, but that's basically what we did. How many standard deviations away from the mean you are. That was 3.09. So we can figure out what that area comes out to be. Small or large, what do we think that area is going to be without looking at the table? It's going to be small. And so how does that compare to your answer in part B where we said, yeah, this would be surprising? They agree, right? Small probability, surprising event. Yeah?
I guess generally, more generally, my question is, I understand with the binomial when you have like exactly like what's probably the 2 out of 5.
Uh-huh.
How does that change when they say like what's the probability that like 2 or more?
So you articulated very well what the difference is. One is an exact probability, and the other one is a range of probability. So we chose to do this using this normal approximation, this part C. Did we have to do that? Is there a way that I could just not bring in the word normal distribution and still calculate this? What do we think?
Yeah, but it would take a long time.
So it would take a long time, so let's not go through all of the details, but let's try to figure out how would I do this using only the binomial distribution. What does 45 or more mean in a sample of 50?
Probability of K equals 45 plus probability of K equals 26.
So this would be K equals 45 or K equals 46 or k equals 47, all the way to k equals 50, right? Each one of these can be calculated with a binomial, right? So we could do that. So here n would be 50, k is 45. Here n would be 50, k is 46. Here n would be 50, k is 47, so on and so forth. I could plug them into the binomial formula, get each one of these probabilities individually, and add them up. That would be equivalent to going about this piece by piece as opposed to doing it as a whole with a smooth distribution. Does that explain?
Yeah, so I guess for when you have 2 out of 5, you're looking for one specific.
You're looking for one specific outcome.
If they say like 2 or more, you want to calculate the z-score using the standard deviation and then do what you would normally do in finding p-value.
So I will interject one other thing here. If you're asked for exactly 2 successes out of n trials, yes, you would just use the binomial distribution and find that. If you're asked for a range, so 2 or more, you can potentially convert it to a normal distribution problem first. I'm only saying potentially because you can only do that if this condition is satisfied. And that condition is only going to be satisfied if you have a sufficiently large sample size. If it's not satisfied, so for example, let's where your n is equal to 5, and let's say k is equal to 0.1, okay? And you're asked for 2 or more successes. I can't convert this into a z-score problem again, because n times p, which is 5 times 0.1, is going to be 0.05. Or sorry, 0.5. It's not greater than 10. I don't have a sufficiently large sample size.
So in that case, I would want to calculate probably 2 out of 5 plus 3 out of 5 plus 4.
Yeah, exactly. Okay? And if you have to do that, right, this would be, the way to do this would be k equals 2, k equals 3, k equals 4, k equals 5. What would be a shorter way of calculating this? Yeah?
1 minus probability of k equals 0 plus k equals 1.
So sometimes when you need to do lengthy calculations like this, it might be smart to stop for a second and think, can I please get away with doing a little bit less work? So then what you might say is, this is what I want. I'm going to calculate what I don't want and just find the complement of that. So it's worthwhile to go through that thought process. Sometimes it might save you time, sometimes it might not, but it might be worthwhile to go through it. That's where we, for example, said that trick can be really helpful when you're looking for at least 1 in any scenario, because this is always going to be 1 minus the probability of none, because those, regardless of what your n is, those are always going to be complements of each other, and it's always going to be less work to calculate k equals 0 compared to any other range of numbers. All right? Yeah?
So is it the same to calculate like 45 or more versus like at most 5 or at least
45 or more is the same sentence as at least 45. Okay? If you're having difficulty with like at least or more, whatever, think of something you care about. If it's money, think about money. If it's something else, think about something else. So I will only do X if somebody gives me at least $45. What does that mean? 45, 46, 47, 44, not cutting it, okay? Sometimes it makes sense to care about some, like put it in context of something you might care about, being like, okay, what does this really mean? If somebody tells me, I'm giving you this task to do, and this should take you at most 3 days, what does that mean? 0, 1, 2, or 3. 4 days, it's going to be too late. Okay?
So
So if you ever see, like, at most or at least, just check the conditions and then use the normal approximation.
If you can,
Yeah.
because that might be less work. And if you can't, then you're going to have to do it the other way around.
On the sample midterm, there was a question that did similar stuff to this, but it's the cat one.
Uh-huh.
But I didn't get, I mean,
Cat is?
is it your cat?
No, it's Maru. You guys don't know who Maru is? Oh my God. Don't look at it tonight. You'll never be studying. Tomorrow, Google Maru. She's a Japanese cat. Very cute. Loves boxes. There are a lot of videos. Yes.
I guess I didn't get what bias towards or against meant, but like in looking at how you actually do it, like it makes sense kind of, but I don't know what.
So let's say that, let's think about something you might care about. Maybe not cat videos. Let's say that you eat at the cafeteria every day and you hate red meat, okay? And when you signed up for this meal plan, you were assured that you would only be served red meat 10% of the days, and other days you would be served something else. At what point are you going to start thinking that information I was giving was wrong? That they're biased towards serving red meat, for example. When you get too many of those in a row or whatever, right? So how do we define too many? I mean, in this case, for example, we're told there are 100 videos that you're going to watch, and the probability that one is a cat video is 0.11. So if you literally use this random video picker to watch 100 videos tonight, and 11 of them are cat videos, you're going to say, okay, it did exactly what it was going to do. If it picks 12 cat videos, are you going to be super offended and say, oh my God, like that 0.11 was wrong? What about 15? What about 90? What about 20?
So then would it be using what we just said about like unusual observations?
Exactly. So we would be using what we said about unusual observations. If you're going beyond the range of what's usual, what is expected, then we're saying, well, now it's going to be too many or too few. So bias towards or against means either bias towards cat videos means unusually higher number than you expected, and biased against cat videos would mean unusually lower number than you expected. So how would I figure out what that is?
Well, to find mu, you do n times p.
So that's 100 times 0.11.
11. And then standard deviation is 100 times 0.11 times 0.89, or square root of that. And that's 3.13.
So that means that if 11 is in the middle, and I do, oops. If whatever this range comes out to be, any number of videos in here, I can just say, this may have been due to just random chance. Any number of videos outside of that range, I'm going to say, that's an unusually high or unusually low number of videos compared to what I was promised. Okay? Yeah?
I just have like a logistical.
Uh-huh.
Are there any other sample midterms that we can look at, or?
Mm-mm. I don't have other sample midterms. Yeah. Something that if you haven't yet gone through them, there are those questions on the Coursera with the videos that you're welcome to try. And those are not graded or anything like the practice quizzes. Yeah, and once you submit it once, it changes the questions for you. If you take it a few times, you're going to start recognizing the questions, but you can do it multiple times.
Okay.
Yeah?
So how would we calculate the exact range for this, like the exact numbers?
So how would I calculate what is the boundary beyond which I would consider unusual? If my expected value is 11 and my standard deviation is 3.13 and I'm saying anything more than 2 standard deviations away is unusual, how would I calculate these numbers?
How would
So take a look at this graphic. We're saying anything within 2 standard deviations of the mean is okay. Anything beyond that is not okay. If 11 is here and I move 2 standard deviations away from it, how would I calculate what this number is? So 11 plus 3.13 plus 3.13. Right? So this would be 11 plus 2 times 3.13. Does that make sense? That's 2 standard deviations above the mean. What is the boundary here? How would I find that one? Yep. Exactly. Okay? Yeah?
There's one of the application exercises, I was wondering if we could do that. It's 2.3, part 2.
So I'm happy to go over this now, but I did post a video where I do go over it if you guys want to review, okay? So this is part 2. This part. Okay. So we're told that average hourly wage, so this is, hold on,
What's the number 4?
app x 2.3, which one?
Number 4 and 6 within this.
Okay, so number 4. Suppose that a worker applies for a manufacturing job in North Carolina and receives the good news that she got the job and that her pay will be at least $16.50 per hour. She would really like to be able to make at least $17 per hour. What's the probability that she will get what she wants? Okay? So how would I calculate what's the probability that she will get what she wants, given that I already know that she's making at least $16.50? How would I put this in probability notation?
Probability of at least 17 given 16, getting 16.
So if I say X is however much money she makes, this is how I could write it as, right? So how do I calculate this conditional probability? Think about it as this is event A and this is event B. Okay? What does Bayes' theorem tell me? If I'm looking for A given B, that's probability of A and B over probability of B. Right? So how could I write that in context of this problem? What goes in the denominator? In the numerator.
Probability of getting 17 and 16. Or great X, that X is
Mm-hmm.
greater than 17 and X is greater than 16.50.
Can't you just say x is greater than 17?
We'll get there. What goes in the denominator?
The probability that X is greater than 16.50.
So now we need to figure out how to reason through this. Somebody is making more than 17 and more than 16.50. How much money are they really making? More than 17, right? Because really what we're saying is, if this is a distribution, that a person is both here and here. Any person that are in both the black and the red regions, they're basically in the red region, right? So this is the probability that they make more than 17 divided by the probability that they make more than 16.50. And each of those, we had said earlier that we can calculate with a normal distribution. Okay? What was number 6 here? Okay, in number 6, we're told if 34% of New York manufacturing workers make more than $19 per hour, what is the probability that in a random sample of 100 New York manufacturing workers, less than 30% make more than $19 per hour? So what are the things that are given to me? Probability of making X being greater than 19 is 0.34, right? That's one thing that's given to me. We're told that we have 100 people, and we're looking to see what's the probability that K is what? The number of successes is what out of 100? 30 or less, right? Yeah, I will show it in a second. I can't show both. Okay, all right? So this is basically the situation, right? So the probability of success is 0.34, N is 100, and this is the range that I'm looking for.
And we would just do normal approximation.
We probably want to be able to do a normal approximation, because otherwise, if I had to do this piece by piece, I would need to calculate probability that K is equal to 0, 1, 2, 3, and add all of them up. So if we can do the normal approximation, that'll save us a bunch of time. How do I check if I can do the normal approximation?
100 times 0.34.
And 100 times 0.66, right? 1 minus 0.34 should both be greater than 10, and indeed they will be. So if that's the case, we said we can do a normal approximation. That means I'm going to draw a normal curve. And whenever I draw a normal curve, I want to mark my center. What do I put in my center? 34. And then I want to mark the range that I'm interested in. Where do I shade? Here, right? So that becomes a problem we're a little more familiar with now. Area under the curve, I need a z-score. I'm going to need to find one other thing before I can calculate everything I need, which would be the standard deviation that we did a few times so far. Okay? So we have a few minutes late. Few minutes left, not late. So what other questions? Let's get your 2 questions. Yeah.
Just a basic one. I think in one of the problems, in the first problems, it was like if the probability of flipping a coin, or it got heads 8 times, is it less probable to get a head the next time? And like in that flip, it's still 50%. But overall, isn't there a smaller chance? Because like if you did a probability tree, it'd be like heads, heads, heads. It'd be 0.5 to the 8th, like to the 9th.
So if you're flipping a coin many, many times,
Yeah.
right? And you're looking to see what's the probability of the next flip. And even if you think about it as a probability tree structure, you want to picture yourself at the beginning of one of those branches. Not as a joint probability at the end, but we're thinking about it as what is the probability for the next step. That's always 0.5. Now, it is true that if you have a fair coin and it's constantly coming up heads, that there might be something wrong with it. But that's looking at it retrospectively at the sequence of events. For any coin, at any given time, the probability for the next flip is always going to be 0.5 for a head or a tail. If you do have a coin that consistently comes out heads, you flip it 1,000 times and it's still heads, you should be concerned about how fair that coin is, probably. Okay? Yeah?
This is from the practice midterm, problem 9.
Yes? You just want to go through this problem, or did you have a specific question?
I got 2 of them, but I didn't know why the margin of error, why that would be also.
Okay, so we have a random sample of some 1,000-something adults. 11% say they approve of the way the Congress is handling its job, and we have a 95% confidence interval from 7 to 15%, right? So 0.11 is in the center, lower bound is 0.07, upper bound is 0.50, right? Is it true that the population proportion is 0.11? No. If I wanted to make this statement correct, how could I correct that statement? So if I said the sample proportion is 0.11, that would be correct. What's another way I could make this statement correct? That population proportion is possibly 0.11, or population proportion is unknown. All of these would work. But what is equal to 0.11 is my p hat. That is my sample proportion. So this one is not correct. The sample proportion is 0.11. That we said is correct. So this is correct. The margin of error is 0.04. What do we think? How do I construct a confidence interval? Sample statistic plus or minus a margin of error. So basically, whatever this distance is, that should be my margin of error. And indeed, that looks like that's 0.04, right? 95% of random samples will have sample means between 7 and 15%. What do we think? Think back to the last lab that you guys did, right, with the confidence intervals, when you are constructing many, many confidence intervals there. What we care about is, what does change is every time you take a sample, that confidence interval is going to change. We don't care about where those new sample means or sample proportions in this case is going to be. That's not of interest to us. When I get a new sample, I can directly calculate a new sample proportion. What we worry about is whether these confidence intervals will contain the true population proportion or not. So if I wanted to make this statement correct, I would say 95% of random samples with n equals 1048 will have will contain the true population proportion. Does that make sense? That's the definition of a 95% confidence level. Yes?
Oh, so if the prompt had said that it was a 95% confidence level, would that one be true or?
No, basically that sentence is not true at all. If we wanted to figure out what is the definition of a confidence level, that would be what I just corrected it to. The confidence level is not about whether a future sample will fall in it or not. That's not of interest to us. We never try to do inference about samples, because when you collect a future sample, you can calculate all of its statistics. That's not interesting. What we're trying to figure out is, will a future confidence interval contain the true population proportion or not? Does that make sense? It is possible that the population proportion is 0.18. True or false?
True.
Yeah, it's possible. Is it very likely? I think we're saying it's probably not very likely, because we said we're 95% confident that that true proportion is somewhere between 7 and 15%, but it's absolutely possible that the true population proportion is outside.
For the fourth part,
Mm-hmm.
is it possible to correct that statement and keep between 0.07 and 0.15?
No, there wouldn't be a way that I can think of that would correct that statement and still keep this bit, because what that bit is about, between 7 and 15%, happens to be about this one sample you happen to have taken. So it's not, just because you got this sample and this confidence interval, that shouldn't dictate what might happen with just another sample from the population.
And what if you try to create a statement that was 95% of confidence intervals, could you say something about the values in there?
No, we have no idea where those future confidence intervals are going to be, nor do we care, because when you get a future sample, you can calculate what they're going to be. And basically, as long as you're not making a calculation error, statistically that's not interesting. All we care about is wherever those confidence intervals might lay, 95% of them would contain the true population proportion and the rest wouldn't. Yeah?
Is it valid to do something like, so you calculate the interval for one sample, and then you calculate for another, and then where they're overlapping? So if you calculate variance, can you shrink your interval by knowing where they? So I mean, if you calculate thousands of them, you probably there's a point where you know the mean is, right?
Not necessarily. So if you calculate thousands of intervals and they're going to be all over the place, but there will be some overlapping areas. So it is true that chances are the true population proportion is somewhere where about 95% of them overlap. You won't know exactly what it is because it's a continuous distribution, so it's not going to be exact. But wherever about 95% of them overlap, if you can think of some band, that's probably where your true population distribution is,
So
true population proportion is.
If I did another sample and it gave me from, I don't know, like 0.05 to 0.13, I don't know. Could I shrink my interval
No.
to like 0.0?
No. So if you got another confidence interval, and let's say it was like this, okay? So what you're asking is, could you then shrink your interval to be just this much, right?
No, but you can't. I don't know.
Is that what you meant?
Yes, that's what
No, but you can't do that, not just with two intervals. What we're saying is if you had thousands of these, as in law of large numbers, you want a lot of them, and you looked at where about 95% of them overlap, that would be a region where your true population proportion is going to be found. But you wouldn't want to do that just with a couple of intervals.
too high risk.
Yes, it would be too high risk, exactly.
For question number 17.
Let me see, are there any other questions on this? Okay, let's do this and then go to 17. Determine the following statements, if they're true or false, and circle the appropriate letter. Both of them? I mean, I can if you want, but. Okay, so increasing alpha increases the power of the test. What do we think? We were talking about this just yesterday in class. What is alpha? What's the definition of alpha? That's the probability of a type 1 error, right? And beta is probability of a type 2 error. And 1 minus beta is the power, right? And we said that if you increase alpha, your beta is going to go down. Because we said that they go in opposite directions. So if we talked about how if we want to keep both of them down, we need to change our data set. So if beta goes down, what happens to 1 minus beta? It goes up. So then basically, as my alpha increases, the power of my test increases as well. Again, this seems like, oh, well, isn't this a cheap way of just increasing your power? Sure, it is. But now you're actually also increasing your probability of making a type 1 error. We talked in the other question how a type 1 error could be the reason why the FDA sends out a non-beneficial drug and potentially kills people. So yes, you can, but you are also increasing your risk of making another mistake. Yeah?
Alpha is also the same as the significance level.
Alpha is also the same as the significance level, yes. So that means that a test that is more generous in terms of how you can reject the p-value, a higher alpha, has a higher type 1 error rate. And since the power is about correctly but rejecting the null hypothesis, since it's about rejecting it, the more likely you are to reject, the higher your power is. Does that explain part A? Okay, in part B we said you're going to collect income data from a right-skewed distribution of incomes of politicians. If you take a large enough sample, the distribution of the incomes of the individuals in this sample will be nearly normal. What do we think? No. That's not going to be nearly normal, right? Because we're talking about a distribution of individual observations. I mean, think about it. We have talked about in class, for example, you take a sample of people from the US, they're going to have a right-skewed income distribution, right? That's just how things work. in most countries. Just because you took a bigger sample of people, that's not going to change the shape of your population distribution. Now, I recognize that there has been instances where we have made statements like, oh, the population distribution is right skewed, but we have a large enough sample size, so blah will be nearly normal. What is that blah? The sampling distribution. So if we were actually, instead of recording incomes of individual people, but what we were doing is instead take a large sample of politicians where the distribution is right skewed, find their mean, save that number. Do another one, save that number. And you build up these means, that sampling distribution according to the central limit theorem will be nearly normal, but the individual samples are still going to reflect their parent population. So that's why in class when we were going through some of the stuff with the central limit theorem, I tried to stop people from using the word it. You should always stop yourself from saying ever, it is normal. Always say what is normal, and then you won't be confused. The population distribution, right skewed. The sampling distribution may be normal if you have a sufficiently large sample size. Yeah?
Is this one sample called sample distribution? So there's population distribution, sample distribution, and then sampling distribution?
Yes, population distribution if we had data from all politicians. Sample distributions if we have data from a sample size of n. And sampling distribution would be if we had the mean of from one sample and another one and another one and another one, and we built up that distribution. Yeah?
Is saying that alpha is equal to the probability of the type 1 error the same as saying that it's alpha is equal to the probability of the type 1 error given the null is true?
Yes. Yes, exactly.
Is that also equal to saying that there's a 90% confidence interval? Like a significance level?
How'd you come up with 90%?
1 minus 0.9.
What's 0.9?
1, sorry.
So you're assuming alpha is 0.1?
Yeah, if alpha is 0.1, then with the confidence interval, 90%.
If we have a hypothesis test, so if I have a hypothesis, alpha is 0.1, what is the equivalent confidence level? I can't answer that question. I need one more piece of information.
Looking at the hypothesis is one-sided or two-sided?
Exactly. So if the alpha is 0.1 and I have a one-sided alternative hypothesis, then what would this look like? So maybe the figure looks something like this, where this is 0.1. What is the equivalent confidence level here?
0.1 or 0.8.
In this case, it would be 0.8. If I had a two-sided HA, then it would look something like this, where the 0.1 is made up of two components. And here the confidence level would be 0.9. Yeah?
The two-sided alternative hypothesis would always say a particular number is not equal.
Exactly. And the one-sided would say less than or greater than. You had a question on number 17.
Yes.
Is that right?
Why?
Yeah?
I'm just unclear as to where.
Okay, everyone else in this room is going to tell you how. So let's explain. How do we go about? Give me your answer for A, and then that might be easier.
Type 1.
Type 1. So is that clear why that's type 1?
Yeah.
Okay. So let's say that today, if I have a drug test, whatever like this, a hypothesis test for a drug, and I accidentally release it to the market, what's the probability that I do that? What's the probability of committing a type 1 error? The significance level. So for any given test, the probability of making that mistake that's described in part B is indeed the significance level. But the answer to this question wasn't 0.025.
It was squared.
It was squared. Why? Because we're looking at two independent tests. So basically what it's saying is you're going to have two different hypothesis tests. And in the first one, you want a type 1 error. And in the second one, you want a type 1 error. And these are independent of each other. That's what the instructions say. So for the square root of n, right? And square root of n is always going to be some positive number greater than 1. And hence, we know for a fact that standard error is always less than standard deviation. So we know, for example, already that B cannot be standard error, right? Because that's the largest one. We know that standard error is definitely not the largest one of these things. What else do I know?
The confidence interval has to be larger than the standard error because you're going to have to multiply it by 1.96.
Exactly. This is a 95% confidence interval. So my margin of error has to be greater than my standard error because margin of error is 1.96 times the standard error. So standard error is also smaller than the margin of error, right? So I need one last piece of information because this still doesn't tell me how the standard deviation and margin of error compare to each other, right? So let's try to write things out in a way that tells me something about the margin of error and the standard error. So my margin of error is 1.96 times s over square root of n. How can I use this to decide which one is bigger? Yeah?
Can't you say basically as long as n is like bigger than 4, your margin of error is going to be larger than your standard deviation? Because, I mean, if n is 4 and you take the square root of n, it's 2, so it kind of cancels out the 1.96, which makes your margin of error equal to s.
Exactly.
So your n would be larger.
Exactly. So with any n bigger than about 4, which is, so you're just rounding the 1.96 to roughly 2, saying let me square that, that would be 4. Anything other than that, your standard deviation is going to have to be greater than your margin of error. So that would be a really great way of reasoning about this. Another way would be if you're not seeing that, that number 4 doesn't jump out to you, and you need to get an idea about what n is at the end of the day to make a conclusion about this. What do you think n is in this situation? Roughly. We don't really need it exactly, but roughly. How could I figure that out? We can count the dots, right? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29. I'm counting 29 dots. So what this means is my margin of error is equal to 1.96 divided by square root of 29 times s. Right? I just moved that square root over. Why did I do that? Because if I actually then go ahead and calculate this, 1.96 divided by square root of 29. So this number comes out to be 0.36. Okay? So your margin of error is equal to 0.36 times your standard deviation. Does everyone follow what we're doing? Then which one is bigger? The standard deviation is bigger because you're multiplying it by a fraction, not a number greater than 1. So this also tells me that my margin of error is less than my standard deviation. So if I was to put all of this in order, standard error is smaller than margin of error, which is smaller than standard deviation. So then which one is which? Which one is the standard deviation, A, B, or C? B. Which one is the standard error? A. And the margin of error is then going to be C. Does that make sense? And this is going to be true for really any reasonably sized data because as we just said, as long as your n is greater than like 4, which hopefully it is if you're doing any of this, you're going to have this situation. Okay? Other questions on this? Yeah?
No, this one, but the one right above it.
The one right above it. So let's answer that and then let's go to your question.
That's fine, same question.
Yeah, same question? Okay. So, the FDA says that if a new drug is deemed to be effective, we need 2 independently conducted randomized studies that both show statistically significant benefit from the drug at a significance level of 0.025. Okay? So given that the null hypothesis is that the drug has no benefit, what type of error has been committed if a new drug appears beneficial to the FDA when in fact the drug provides no benefit? What do we think? Type 1, right? So here, basically, you rejected the null hypothesis of no benefit when really you should not have done that. Is that clear for everyone why that's a type 1? Okay, so if that's a type 1 error, if this rule is followed, what is the probability that a new drug will appear beneficial to the FDA when in fact it provides no benefit? What's the probability of making a type 1 error? Alpha is our probability of making a type 1 error. So, should I put that here? We have 2 independent tests, right? So you need test 1 and test 2. And each one of these, you make that mistake. The probability of making that mistake in test 1 is what? 0.025. The probability of making that mistake in the second test is what? If they're independent, then it should also be 0.025. So then what is the probability that this actually gets through the FDA, as in both tests have made this mistake? That's going to be 0.025 squared, because we would multiply these because they're independent events. Okay?
So if it was like 3 independent, you just do it the third time?
We would just do it the third time because we would have one other test that has to pass through at that rate. Other questions? Yeah?
For number 7.
On this?
Yes.
Oh. Okay. So we have this Gallup poll results, and this is just a screenshot from Gallup.com. This is what they posted. So we're looking to see this 73%. What is that the probability of? How would I go about reasoning through what that is the probability of? It obviously has to do something with 18 to 29 years and something with against, but that doesn't really help me, right? With these options. Yeah?
It's the probability that adults between the ages of 18 and 29 years are against this particular.
So probability that 18 to 29-year-olds are against. So would that be C or D or E? Because they have all of them.
Oh,
D?
D.
D? How do I know? Yeah?
I just look for like what adds up to 100.
Exactly.
So the 27 and 73 adds up to 100, which is the 18 to 29, which
So
is your.
if you basically, do this, you'll see that across the rows we add up to 100. That means that these proportions are over a given row. What's the probability of being in that cell? If the numbers added up to 100 going down, then that would be against given 18 to 29. Okay? So that's how we would read that. Oh, sorry.
D.
The other way around. D, yeah.
Can you explain that one more time?
So we are told that something is 73%, right? And another thing you could be is you could be 4 and you would be in the 27%, right? Basically, we're categorizing 18 to 29-year-olds into 2 categories. Either you are for or against, nobody said no opinion. How do I know that this distribution is given the age range? Like, what's your answer given the age range? we look to see where your percentages add up to 100. Since the rows add up to 100, that means we took a subpopulation of 18 to 29-year-olds, and then we looked amongst them to see which percent were against. If this was the other way around, if C was the answer, we would have first taken a subpopulation of people who are against and then looked among them what percent were 18 to 29, what percent were 30 to 49, 50 to 64, 65 plus. So these proportions would have added up to 100, which clearly is not the case here. Other questions? Yeah?
I'm sorry to bring this up again, but you said earlier that in no instance would a like a 95% confidence statement include the calculated intervals for that 95% confidence level.
So what I said was not that if you calculate a confidence interval, so let's say that you calculate a confidence interval for, what was it, the proportion of people who approve of the Congress's job, right? And you calculate that to be between 0.07 to 0.15, right?
Yeah.
How would I interpret the confidence interval? We are 95% confident that 7 to 15% of Americans approve of the job the Congress is doing. Indeed, I did mention those numbers. But if you're asking about what does a 95% level mean, that is not about this particular interval anymore. That's more of a conceptual question than a question about the particular data set. What does a 95% interval mean? What it means is that if you take many, many samples of the same sample size and you continue to construct confidence intervals for them, which will each be slightly different, about 95% of these will include the true population proportion and about 5% of them will not. In practice, you would never do this. You would never go and calculate many, many more confidence intervals because that would require that you take many, many new samples, right? So that's more of a conceptual answer about what does 95% confidence level mean. And the example we gave in class was, it means something very precise. Like some people say things like that in life, like I'm 80% confident, blah, blah, but they're just making up those numbers. Like they're making up a high or a low number depending on their degree of belief, but they're making up the number. In this case, that 95% doesn't just mean I'm pretty confident. It has a very specific meaning. Yeah?
However, and this is in relation to the lab that we have
Uh-huh.
for this week, I think, so like the one we did. It doesn't, like for example, we did 50 samples, right?
Mhm.
So 95% of 50 samples would have been like 47.5,
Uh-huh.
which is something you can't really have. So we got like 47, so people must like maybe got 45. Like you don't get exactly those.
You don't get exactly that number unless your number of confidence intervals is infinitely large. So that's what you would expect to happen at the limit. That's
So
the
this
law
is,
of
like,
large
law
numbers.
of large numbers.
Exactly. Mm-hmm.
So you get around, I mean, you're not going to get 2.
Yes,
You know, you're
exactly.
getting around 40 something.
Exactly.
Because it's still like a small number. Like it's a sample of intervals, is that how
Exactly. You can think about it as a sample of intervals as opposed to all possible intervals you could have gotten from that population for that sample size.
But there's never like a limit for how many, like there's not an all number